Okay, hello everyone. Thank you for coming today. I'm Fan, a PhD candidate at UIUC. Today I'm going to present our work LinkTeller, a privacy attack on graph neural networks. Our work is inspired by a real-world industrial example which we observed in an international IT company. So this company, similar to others, is consisted of multiple teams: the product teams, the advertising team, and the information security team. Different teams have different functionalities and they hold different information. The product team specifically hold the user information in each product, which can be viewed as the features of the users. The advertising team holds the user network, essentially which user is connected to which other user. And one role of the information security team is to regulate the information flow between the different teams in their company. Here we would emphasize that in their company, the user network among the entire company is treated as the confidential information. It is not publicly accessible and cannot be obtained by any other team in their company. But from the viewpoint of the product team, it is beneficial to incorporate the user network into their machine learning models. So how can the product team possibly incorporate the user network? We already know that the user network cannot be leaked outside of the advertising team. We also know that it is fun to exchange the user information among the teams. So the solution in their company is that they build a local model at the advertising team, which is trained with both teams' information, and then they release the trained API. When the product team queries the API with the input of a set of users of their own product, the API will return the corresponding predictions. And same for product B. Actually, the local model is open to any team that submits queries with any set of users. Here we provide an abstraction of the example we just showed. What we consider is actually the vertically partitioned graph, where different parts of the graph belong to different data holders. Let Alice be the advertising team that holds the user network, and Bob be the product team that holds the user information. At the first communication stage, Bob would send the user information represented as node features and labels to Alice. Then Alice uses the node information received from Bob as well as her own edge information to train a graph neural network. After the model is trained, Alice releases the API. Finally, in the inference stage, Bob or any other user can query the API with any possible set of nodes. Against this background, we are particularly concerned with the risks of edge privacy. Even though this solution is designed to protect the edges from being leaked, how effective is this solution? Will the inference API still leak the private edges? Second, we wonder whether the risks can be ameliorated if there does exist concerns of edge privacy. Let me first provide a quick recap of the related work and the preliminaries. Graph neural networks are widely used in semi-supervised node classification. It takes input represented by nodes and edges and outputs the predictions for nodes. And graph convolutional network is one specific type of graph neural network that uses the graph convolutional operator as the aggregator. In the literature, there are mainly three types of privacy attacks on graphs. They target at different components. Here, our focus is the link re-identification attack that targets the edges. There are a few works in the pre-graph neural network era that uses either the probabilistic models or explore the local graph features. But after the graph neural networks came into play, there are a lot of adversarial attacks on graphs, but not many privacy attacks. The existing works either operate on the node embedding level or require very strong prior knowledge on the attacker's knowledge and their assumptions. So our challenge here is to design attacks on black box graph neural network APIs with minimal assumption on attackers' knowledge. Here is an overview of our work. We propose LinkTeller, the edge re-identification attack against the black box graph neural networks. It is a query-based attack, and the attack idea is inspired by the influence propagation in the network. Next, to see how effective our attack is, we consider a countermeasure of the attack by incorporating differential privacy into our model. We introduce our algorithm and provide the analysis. Last but not least, we conduct extensive experiments to evaluate our proposed methods. Let's start with the LinkTeller part. Here is the formal interaction model we consider. Alice receives the node information and then trains the model using both nodes and edges. The released API is open to query. After Bob queries the API on the set of interested nodes and obtains the corresponding predictions, he launches the LinkTeller attack, which reveals the edges in the graph. We consider only the elementary knowledge and capability of the attacker. We only require query access to the black box API during inference time, and we do not assume any knowledge of either the partial graph or the shadow datasets as in the baseline LSA attack. The attacker's goal is to recover the connections among the inference node that he has interest in, and the means is to query the API and perform some magic on the return predictions. So how can we perform the magic? Let me picture the intuition of the attack. We already know that the graph structure plays an important role in the graph neural networks. In each layer of the network, the information propagates from each node to its adjacent nodes along the edges. Let's take one example here. For the blue node, in the first layer, its information will flow along the orange arrows, and in the second layer, the information will flow along the orange arrows. So we can see that the connection in the graph determine whether the information of one node can influence the other and how strong the influence will be. Therefore, if we can somehow compute the influence value of one node on the other, we will be able to tell whether there exists an edge. Here comes our algorithm. First, we calculate the pairwise influence values among all node pairs. Then, for the pairs with the values above certain thresholds, we predict them as edges. Till now, our question is, how do we exactly compute this influence value? We concretely present the steps to compute the influence values here. Our approach shares some flavor of finite difference analysis or the perturbation-based analysis. For the inference node set Vi with the original node features X, let the current considered node be V. We perturb its features by upweighting it by an infinitesimal amount of value. Then we invoke the API twice for the two different node feature matrix to obtain two different prediction matrix. By taking the difference between the two, we obtain the influence matrix, and then the row norms of the matrix are exactly the influence value between the node V and all other nodes. The influence value we obtained actually comes with several nice properties. Here we present a case study on graph convolutional network. First, we have the conclusion that in one-layer graph convolutional network, whenever the pair of nodes are unconnected, the influence value will be 0. Furthermore, on k-layer graph convolutional network, whenever two nodes are at least k+1 hops away, the influence value will be 0. So these two conclusions, they serve as a complement to our intuition, and they better support our algorithm. Now we can move on to the second part where we aim to further investigate the effectiveness of LinkTeller by studying a potential countermeasure of it. Since we want to protect the edges, we consider the notion of edge differential privacy, which guarantees that by looking at the DP algorithm output, we cannot tell which one is the input to the algorithm, the left or the right. Here, the parameter epsilon quantifies how rigorous the guarantee is. We can view it by how much privacy is leaked. Thus, smaller epsilon implies stronger privacy. To enforce edge DP in the graph convolutional network, we propose the following framework based on input perturbation. So during training, we first perturb the original training graph via a DP scheme M epsilon. Then we perform standard training on the perturbed graph and release the API. During inference, we apply the same perturbation scheme and invoke the API with the perturbed inference graph. We note that all processes here, including the perturbing training inference, they are all performed at the local center, and they are transparent to the API caller. The final predictions after all these operations are returned to the API caller. Particularly, we designed the DP scheme such that It guarantees the indistinguishability between the perturbed graph and the original graph. We propose two algorithms that achieve the goal: edge-rand that performs value flipping and lapped graph that adds Laplacian noise. We additionally provide analysis on the privacy as well as the upper bound analysis for any link re-identification attack against our DP graph convolutional network. More details can be found in our paper due to the time limit. Finally, we come to the evaluation part. First of all, we evaluate the effectiveness of our LinkTeller. We experiment with 8 datasets in both the inductive and transductive setting. We tested 2 layers and 3 layers graph convolutional networks and GATs. We follow the literature to train the networks and evaluate the performance of the network via the F1 score of the classification. To evaluate the attack, we use the matrix precision, recall F1 score, and AUC scores. We compare with 2 baseline attacks. We specifically construct several scenarios so that we can evaluate different density beliefs against the nodes of different degree distributions. Here are the results for one dataset among all 8. We can see that for all scenarios, LinkTeller invariably outperformed the baselines. Next, we evaluate LinkTeller against the countermeasure, the DP graph convolutional network. Apart from the same setup as previous, we additionally evaluate 2 DP schemes and 10 privacy budgets. Here we plot the change of F1 score of the attack with the privacy budget epsilon. Lower values means less successful attacks. We see that DP can significantly decrease the attack effectiveness. Yet, when the privacy budget is high, the protection is quite limited. Specifically, we discovered that DP can offer better prediction for the low-degree nodes, which are shown in the first row here. In the end, we analyzed the trade-off between model utility and privacy. The left figure shows the model utility, where higher value means higher utility. The right one shows the privacy, where lower value means better privacy. We see that models with higher utility are more vulnerable to our LinkTeller attack. Furthermore, we note that the comparison can offer some insights on how we can find the sweet spot. In the end, let me show this slide again as a summary. We propose LinkTeller to review the edge privacy risks in the existing system. We also propose countermeasures of the attack. Our extensive evaluation showed the effectiveness of the attack and provide insights for the practitioners. That's all. Thank you for listening, and I'm happy to take any questions.
So we have minutes for questions, so please walk to the mic and state name, affiliation. I can start probably with a couple of questions. And do you see any difference with the graph neural network aggregation operation, and if that influenced your attack at the end of the day?
Yeah, so your question is for different architectures like graph convolutional network or the graph attention network. So our study is mainly inspired by the intuition on the graph convolutional network, and we also tested on the graph attention network, since the intuition of the information propagation along the graph is shared, and we see that in the GATs actually our attack is also it is also successful, but not as successful as on the graph convolutional network, and we have several explanations for that, and more details can be found in our paper.
Okay, thank you. Just on time, and I have another question. I'm just checking on the time, sorry. So my other question is, so you presented many experiments on the performance of the differential privacy GCN, but if it was very quick, the slide was very quick, so performance were a little bit all over the place, like, the F1 score was a little bit all over the place, and I was wondering how much training a differential privacy GCN affect the performance of the model on clean data, so without the attack. Is it still usable?
Okay, I got the problem. Maybe I can quickly show that results if the projection is still enabled?
Yeah.
Yeah, so here for the left figure, we show the model utility, which is exactly the performance on the clean data as you mentioned. And on the right-hand side, it is the attack effectiveness. On the left-hand side, the x-axis is the privacy budget epsilon, and we show that when, for example, in the Twitch RU data, when the privacy budget is around 5 or 6, it is still very usable with a reasonable utility here, right? Does that answer your question?
Yeah, that answers my question. Yeah. Okay. So, if there are no other questions, and I believe that we don't have any questions from online, but let me just double check very quickly. No, doesn't look like. So we can thank our speaker once again. Thank you.
Okay, thank you.